Hi. In this third presentation of the regular sequential circuits playlist, we will look at 8-bit registers. After watching this presentation, I hope that you will be able to write VHDL descriptions for basic n-bit registers and also to create user-defined data types. We will start by looking at the VHDL code for an 8-bit register, which is shown in this slide. In this case, what we are looking at is just a collection of 8 D-type flip-flops that are controlled by the same clock and reset signals. You may still remember the VHDL description that was presented for the D-type flip-flop in a previous presentation, or if you don't, you may take a look at that presentation. But in the case of the 8-bit register that is shown here, and since we do not have an enable input, our description is restricted to the register segment, which, not surprisingly, is quite similar to the corresponding register segment in the D-type flip-flop. Actually, the only difference is the statement used to reset the flip-flops, which in this case acts upon the 8 flip-flops at once. You should keep this statement in mind because we will use it frequently when designing register transfer level circuits. The rest of the code is very much self-explanatory, but you may pause the video at this point to have a more detailed look if you wish. Let's move on to a more elaborate block. A register file, as described here, is a block that contains one input port, which in this case is called the write data input port or the write data bus, and one or more output ports. In this case we have only one output port called the read data bus. And it comprises a number of single registers that may be n bits in width. In this case they are 8-bit registers. As indicated here, we need 2 address buses, one to identify in which register we want to write, and that is the write address bus, and the other one to identify which register we want to read, that is to say, to transport to the read data output port. In this case, it's the read address bus. And finally, we need a write enable signal. Since there is no read enable, what this means is that the read data bus will always contain the value of the register that is addressed by the content of the read address bus. Now, there are 2 things that you should notice particularly in this description. The first one is the generic declaration inside the entity description, which facilitates the modification of this code when we want to design register files with a different number of registers or a different number of bits per register. In this case, V defines the width or the number of bits in each register, and W is used to specify the number of registers according to this expression. This is a convenient way to specify blocks that can easily be customized in later designs. And the second thing that you should pay attention to is the data type that is used to describe the register file. Now, this data type does not exist in the packages declared above, so we need to create what is called a user-defined data type. You will need to do this every now and then, and namely to describe states in finite state machines, as we will see in a later presentation. Now, this user-defined data type is declared in the beginning of the architecture body, as indicated here, and the type statement is used to build a two-dimensional array of standard logic vector data types, or actually an array of arrays. And we can now declare an array underscore register signal, which is of the register file type that we have just defined, and so we use it in our architecture description. We are now ready to look at the full architecture description for the register file block, which is shown in this slide. Again, you can pause the video at this point if you want to have a detailed look at this sequence of VHDL statements, but there are two things that I would like particularly to call your attention to. The first one is the initialization statement for the register file when the reset input is active. We are recursively using the same statement that was used before for the single 8-bit register, as you may remember from a previous slide. And the second thing to notice is that the array index value that is used to identify any register in this structure, as I was saying, the array index value must be of the integer data type. And so, because our address buses were defined as standard logic vector data types, we will need to perform a type conversion. Now, if you take a look at the operators and type descriptions, type conversions table that was shown in an earlier presentation, you will see that there is no direct conversion between standard logic vector and integer. And that is why we have to perform this double type conversion, first from standard logic vector into unsigned, and then from unsigned into integer. And likewise, in the case of reading, we again have to perform from standard logic vector to unsigned and then to integer. Now, before closing, I'd like to leave you with one question, which is how would you modify this description if you needed 2 output ports instead of just 1? Thank you for your attention.